So, hello everyone. Today is the fifth problem solving session for the course Introduction to Laser. So, uh, regarding the query that was asked in the last problem solving session, some people asked about the videos recordings and the notes for the problem solving session. So, as I have asked the NPTEL team, and they said me that they have already uploaded all the contents in the NPTEL portal, and I checked that there is a link for those videos. Like, it was written like this: problem solving session August 2023, something like this. If you check the NPTEL portal, you will find this name at the left side of your screen. Okay, so there you will find the Google Drive link for the notes and the previous video lecture. Okay, so I will repeat this information again at the end of the today's discussion, because there is a possibility that few new people join this class late. So I will start with today's class with the discussion of cavity modes. Counting the number of cavity modes. So start with assuming a cavity that is rectangular in shape. So assume a cavity that is rectangular in shape with dimension Lx, Ly and Lz. So the modes we are talking about are basically standing wave inside the cavity. So we need to count the number of standing waves inside the cavity. So the process of counting this mode is start with the property of the electromagnetic wave, that is, when we represent this part ikx, this part is a part of the electromagnetic wave. So here there is a three dimension Lx, Ly, Lz. So xyz dimension. So we will be bothered about this particular term, e to the power minus iota kx Lx plus ky Ly plus kz lz. Okay, so this is basically oscillating function in space. Space means x, y, z. And when we are talking about number of modes in a cavity, we will be bothered about the spatial dependence. So this is the part where the electromagnetic wave is oscillating in space. Also in electromagnetic wave there is another term, that is e to the power I omega t. So this is the oscillating term in time, and this is the oscillating term in space. So now this particular part is the minus I kx lx plus ky ly plus kz lz should be periodic in L. So inside a box, if there is a standing wave, the modes will be counted like this. This is one mode, then this is another mode, then this is another mode. So the thing is that this oscillating wave or standing wave should be zero at the boundary and has a periodicity L. So by periodicity, what do we mean? We mean that there is a full wave in this distance L. So from here to here, this is L, then again this wave will repeat. So this is the periodicity of the standing wave. So basically the boundary condition is that field to be periodic in L and also 0 at the boundary. Okay, so in order to satisfy these two conditions, the exponential integral this part is needed to be equal to 0. So for in x direction, kx lx equal to n phi. So basically e to the power I kx, from here the condition will be kx equal to n phi. So kl equal to n phi. So kx lx n phi. For y it will be ky ly equal to n pi. Then for z it will be kz lz equal to n pi. Sorry, let's just distinguish this n. This one is nx, ny and nz. So these are the number of modes. So now this value nx, ny, nz can have value 0, 1, 2 dot dot dot. Now so the mode number can be specified by the value of nx, ny, nz. Now k square equal to kx square ky square plus kz square equal to nx pi by lx square ny pi by ly square plus nz pi by lz square. So now number of modes in x direction would be nx nx equal to lx by lambda by 2. So similarly for ny, ly equal to lambda by 2 and z equal to 2. Now value of nx can be 1, ny equal to 2 and z equal to 1. So this particular combination describe one mode. So now this nx, ny and nz, these three variable actually creates a three-dimensional space. Okay, now in this three-dimensional space there will be a maximum value of every axis in every axis, so it will create an ellipsoid type of thing. Where this origin will be 0 0 0, then there will be this is nx, nz and this is ny. So now in order to have the total number of mode, we need to calculate the value of this ellipsoid. Now this is the only one octant of the ellipsoid, which is the 1/8 of the whole volume. So volume of the octant is 1/8 4 pi by 3 nx, ny, nz. So in case of a circle, in case of a sphere, we the volume of sphere. is 4 pi by 3 r cube. So r is the radius of that sphere, so this is the volume. So similarly for ellipsoid, that is 4 pi by 3. Then here there is three different value of r in three different directions, so nx, ny, nz. So this is the volume of the octane. So now here we have the value of nx, ny, and nz. 1 by 8, 4 pi by 3, 2 lx by lambda, 2 ly by lambda, 2 lz by lambda. Okay, so this will give this 8 will just go away. So 4 pi by 3 lambda cube lx, ly, lz. Now we are considering, initially we are considering a cavity that has a dimension of lx by ly by lz. So that will actually be the volume of the cavity. So it will be v, which can also be written like this: eta cube mu cube by 3c cube v. So I have just replaced lambda by c by eta mu. Okay, so now we denote this quantity with the letter m. So this calculation defines the number of modes for all frequency up to and including the frequency nu in volume v. Okay, so now there is a thing, that is the, when we are talking about the electromagnetic wave, then there we know that electromagnetic wave can have two polarization, two orthogonal polarization. So for that reason the spatial mode, the number of spatial mode will be doubled. So basically the total number of mode will be 2n. Okay, so now from here we can calculate the mode density, which is generally denoted by the variable rho, which is known as number of modes per unit volume. So then we have rho nu equal to 2n by v, 8 pi eta cube mu cube by 3c. So now this is the mode density in a cavity of volume V. So you might be familiar with this formula from the blackbody radiation. This is how the mode is calculated. Rho nu. Now this rho nu can be differentiated to obtain the number of modes per unit volume within a given frequency interval between nu and nu plus d nu. So in that frequency range, the mode density is 8 pi eta cube nu square ck. So this is the mode density for the frequency interval. For the frequency interval mu and nu plus d nu. So now if we assume the average energy per mode, average energy per mode is kT, then we can obtain the energy density u nu. Energy density u nu of radiation per unit volume within the frequency nu to nu plus d nu. So that will be u nu equal to d rho nu by d nu kt is equal to 8 pi eta cube nu, so nu square c cube kt. So this is known as the Rayleigh-Jeans formula. Now let's extend this calculation in case of light. So consider a beam of light with the intensity per unit frequency at light of intensity per unit frequency is I nu at frequency with a cross-sectional area dA in a time dt. So the energy now the energy density of radiation would be the product of the intensity of the beam, the cross-sectional area, and the time duration. So that will be I nu dA dt. So this will be equal to the energy density multiplied with the volume. So now so this is a volume where this is the I nu, this is the direction z, and the distance is z. So z equal to c dt, and the energy density is u. So now the energy density is multiplied with dV, and then this intensity travels through this medium. So the energy density is I nu dA dt. So here this particular surface has a cross section of dA. Now we can say that the volume dA equal to volume V equal to dA multiplied by Z. Sorry, dV. dV equal to dA multiplied by Z. So I nu dA dt equal to u nu dV, which is I nu dA dt u nu dA dot Z dA cancel out. I nu dt equal to u nu Z equal to c dt. So dt cancel out. So I nu equal to u nu. So when the volume element is in a medium whose index of refraction is eta, then we can write this as I nu equal to u nu c by eta. So we can now convert this expression for the energy density of radiation within a cavity of temperature T to an expression for black body radiation emerging from a hole of unit surface area accessing the cavity and radiating into a hemisphere. As so the radiation from any point within a cavity is traveling in all directions like this, that. So the solid angle is going to be 4 pi solid angle. So the total intensity will be black body will be IB nu equal to integration over 0 to 2 pi, another integration 0 to pi by 2 I nu cos theta sin theta d theta d phi by 4 pi. So this is basically the total intensity radiated in all directions, or it is known as the black body radiation flux. Okay, so this flux is actually obtained by integrating the radiation flux in a direction d omega, so that radiation flux in this direction is I d omega by 4 pi. Now this d omega can be written as I nu cos theta sin theta d theta d phi by 4 pi. So this is written here. So now this is the total radiation flux. Now if we complete the calculation, I BB nu equal to 0 to 2 pi 0 to pi by 2. So this 2 pi and pi by 2 are the limits of theta and phi. So now here what we'll do, we replace this I nu by this relation u nu c. So u nu c, then this cos theta sin theta d theta d phi by 4 pi. So if we the u nu c, this part is independent of this integrating variable theta and phi. So if we calculate this integral, we will have u nu c by 4. Okay, so let's just do one calculation regarding this black body radiation. Compute the radiation flux or power in watts coming from a surface of temperature 300 Kelvin. So this is basically the calculation near room temperature, and area 0.02 meter square over a wavelength interval of 0.1 micrometer at a wavelength 1.0 micrometer. So here we need to compute the radiation flux or power in watts coming from a surface of temperature 300 Kelvin. So the surface is in the near room temperature and the area of the surface is 0.02 meter square, and the wavelength we are considering here has a uh, interval of 0.1 micrometer and the central wavelength is 1 micrometer. So in order to obtain this, what we'll do, we'll have this IBB lambda delta lambda t, then this will be equal to IBB lambda t delta lambda. So basically the flux will be multiplied with the wavelength interval, and here also the surface is provided, so it will be multiplied with delta A. So basically P equal to IBB lambda t delta lambda. So up to this we will obtain a quantity that is watt per meter square, then we will multiply with the area, then we can obtain the power in watts or the radiation flux. So it will become, so this thing, so I'll just write down the expression for IBB lambda t. Is 2 pi c square h by lambda to the power 5 e to the power ch by lambda kt minus 1. This thing comes from the expression IBB nu d nu 2 pi h nu cube by c square d nu by e to the power h nu kt minus 1. So from here we can obtain this. Now P equal to IBB lambda t delta lambda delta A. So this will be 3.75 into 10 to the power minus 22 by 1 into 10 to the power minus 6 to the power whole to the power 5 e to the power 0.0144 by 1 into 10 1 into 10 to the minus 6 into 300 minus 1, then the delta lambda is 0.1, then delta A is 0.02 meter square. So after calculating all of these things, we will have 1.06 into 10 to the minus 15 watt. So at room temperature, the power radiated from a black body with in this within this wavelength region is too small to measure. Okay, so here this is the power radiated from a black body at room temperature, which is almost a order of 10 to the minus 15 watt. So that is femtowatt basically. Any doubt regarding this?
No,
Sorry.
no, sir, no doubt, sir.
Okay. So now, as this is done, we move to the next interesting topic, that is laser with two mirrors. So basically two mirrors. So the mirrors are arranged like this. So the beam continuously go back and forth in this cavity. Now two factor determine so two factors determine if two mirror laser can reach the I set. So I set is the saturation intensity. So the first factor is net gain per round trip. So, the per round trip means that the beam is going here and then after reflecting from here, then it is coming here again. So this is the one round trip. So basically one round trips mean that two reflection. Okay, so in order to so there must be a net gain per round trip of the beam through the amplifier. In other words, all of the losses including transmission losses, scattering losses and absorption loss. So there are three kind of losses that can happen in the uh, two mirror laser, that is the transmission loss, absorption loss scattering loss. So these are the three loss that can happen inside this amplifier. So including all these losses, the total loss should be lower than the gain or increase per round trip through the amplifier. So basically the beam is coming here and going there, and so basically after two reflection there will be certain transmission loss, absorption loss and scattering loss. So these two mirrors are not perfectly ideal. This mirror will have certain amount of transmission. So basically these two mirror will not perfectly reflect back the beam. Some part of the beam will be transmitted through the mirror, some part of the beam will be absorbed by the mirror, and then there will be scattering of the beam. So after these three loss collectively should not be higher than the net gain per round trip. This is one point, and then the second point is sufficient gain duration. So sufficient gain duration. So the gain duration is the amount of time that the gain exists in the amplifier. This so this duration is relevant. This duration is particularly relevant for pulse laser, not for continuous wave laser. So the gain duration is basically when this beam is coming back, uh, is reflecting from one mirror to another. So that is the time duration. So that time duration should have a minimum value. So the gain duration, which is generally denoted by TS. So TS must last long enough to allow a sufficient number of passes of the beam through the amplifier in order for the beam to reach I set. So these two parameters determine the quality of the two mirror laser. So we'll briefly discuss about the net gain per round. So let's assume that a round trip pass of the beam through the amplifier, and assume that the gain is uniform over the amplifier length. So the gain over the amplifier path is not changing over time, so it is constant. In this particular case, the beam will experience an exponential growth for a round trip. So basically that will be G not 2L. So this is the gain factor, and this is the length covered by the beam. 12 for basically the beam is going here and then coming here. Beam is going here and then coming. Okay. Okay. So now for a round trip through the amplifier, it will also experience a loss. So let's include loss at each mirror is 1 minus r. The width of the my pen is smaller. 1 minus r. So basically this is the mirror. This is the beam and it gets reflected from the mirror. Then so the reflectivity of the mirror is r. So the loss will be 1 minus r. So the loss at each mirror is 1 minus r, where r is the mirror reflectivity, and the beam will be reduced by the factor of r after it is reflected from each mirror. The minimum round tips. So for simple situation in which both mirrors have the same reflectivity, it will have become r square e to the power g threshold 2l equal to 1. So what's happening? This is the gain and this is the loss. So for simple situation, these two is actually compensating each other. Then r square multiplied by e to the power g th 2l equal to 1. Then we can calculate the g th equal to 1 by 2l ln 1 by r square. So any gain that is that has a higher value than this GTH will cause the beam to grow. G greater than GTH will lead to the beam to grow. So we can again calculate this for a more general case. So in more general case, here what we have considered that both mirror has same reflectivity. So in this case this one has r and this one also has r, but in general case this one has r1 and this one is r2, and r1 not equal to r2. So these two mirrors have different reflectivity. Also we will consider some losses, that is from for different reason, any kind of losses which is included in these two factor from the mirror, a1 at mirror 1 and a2 at mirror 2, a1 and 2. Then this equals, then and then there is another absorption or loss in the medium. So there is the medium and this medium will absorb some part of the light. So this is a more realistic situation that is denoted by the alpha. So for this general case, the equation will become r1 multiplied by r2, then 1 minus a1, 1 minus a2, then to the power gth minus alpha 12 equal to 1. Then so this is the reflectivity of first mirrors, reflectivity of the second mirror. Then this is 1 minus a1 is the beam that is survived after suffering the loss a1 from the mirror 1, and this is the part of the beam that suffered from after the reflection from the mirror 2, and this is the gain, which is also has a loss c part, that is alpha e to the power minus alpha 12. So multiplying all these terms that should be equal to 1 to find out the threshold gain. So if we can simplify this equation, the gth will be 1 by 12 ln 1 by r1 or 2 1 minus a1 1 minus a2 plus alpha. So here we need to understand that the g naught we talk about should be greater than this gth in order to have amplified beam. So at this particular value gth, it actually the beam entering the amplifier part will and the beam emitting or exiting from the amplifier part will be equal. So if the cavity has a gain of gth that is equal to the gain threshold of the cavity, then the beam will not be amplified. It has to be greater than the gth value. So I will just note down some amplifier parameters for various laser. Laser gth and ts, and the length of the gain medium. Helium neon laser, which is the most common laser, that is a gain. Okay, so helium neon laser has a gain threshold of 0.1, where the unit of the gain threshold is meter inverse. The small gain duration is given by ts in second. So this is meter inverse 0.15. ts is 2.7 into 10 to the power minus 7 second, and the length is 0.2. Then another laser is argon, which is a gain threshold 0.5, length 1 meter, and gain duration is 8.8 into 10 power minus 8. These values are typically for the laser they have checked, so it might be different in different circumstances. Then helium, cadmium, or HCD laser, the gain threshold is 0.3, 1.6 into 10 power minus 7. Then the length is 0.5. Then you can talk about the CO2 laser that has a gain threshold 0.9. Then the TS is 4.8 into 10 power minus 8, and the length is 1 meter. Then ND arc laser, that has a gain threshold 10, and the gain duration is 10 to the minus 8, and the length is 0.1. Then ND glass, gain threshold 3, gain duration 3.4 into 10 to the minus 8, and the length is 1. So these are the amplifier parameters for various laser. So now regarding this cavity, let's see work out one problem. So the problem is as follows. For a cavity with mirrors having reflectivities of 98%, what would be what would the minimum gain need to be in order for the laser to reach threshold if the amplifier length is 1.2 meter and the mirror separation is 0.4 meter. So here the problem is that the mirror has same reflectivity of 98% and the amplifier length is 0.2 meter and the mirror separation is 0.4, and here there is as one assumption that no losses in the cavity other than the mirror transmission losses. So that statement means that the only 2% of the beam is lost after one reflection. So let's start with this. R equal to 0.98 the reflectivity, L equal to 0.2 meter and D equal to 0.4. So GTH equal to 1 by 2L ln. So this is the most simple case. We'll just use the most simple version of the formula. 1 by 2.2 ln 1 by 0.98 on square. So this is 0.4 and 4.04 into 10 minus 2, that will be 0.101. So this is the gain. So in this context there can be another form of the formula. If there is no other losses, then this can be 1 by 2L 1 by 2L ln 1 by R1 R2. So here basically there are no other losses considered, but the reflectivity of the two mirrors are different. One has a reflectivity of R1 and another has a reflectivity of R2. Now let's see another problem. This has a little bigger statement. So if you were to design a solid state laser, so I'll just mention the keywords that is relevant here. This is third image. Solid state laser. If you were to design a solid state laser that reached ISAT when pumped, and if the gain medium, which is a solid state crystal, was limited to a length of 10 cm. Gain medium length, what would be the minimum single pass small signal exponential gain have to be at linear line center if the gain duration lasts only 10 nanoseconds. Assume a rod diameter of 6 mm. So the gain gain duration is 10 nanosecond. The rod diameter is 6 mm, and that the mirrors are 100% reflecting and coated onto the ends of the laser rod. The mirrors are 100% reflecting and coated onto the ends of the laser rod. Assume also that the crystal has an index of refraction 2. So eta equal to 2. These are the parameters that given in the problem. So let's just use the solid state laser L equal to 10 centimeter or 0.1 meter. TA small signal gain duration is 10 to nanosecond, which is 10 to the minus 8 second basically. TA equal to 6 mm, is 6 into 10 to the minus 3 meter. Then eta equal to 2. So number of passes allowed TS CL by eta equal to 10 to the minus 8 into 3 into 10 to the 8 by 0.1 2.0, which will give basically 15 passes. So 15 passes allowed. So that is the one part, first part of the problem. And the second part of the problem is what is the value of the gain. So we have to find G0 L. We will start from e to the power 15 G0 L. So here this is the 15 passes and this is the gain after each passes. So e to the power 15 G0 L is 15 L by dA whole square. So from there the G0 equal to ln 16 in LA dA whole square by 15 L is equal to ln 16 1.5 6 into 10 minus 3 square by 1.5 is equal to 9.21 per meter. So then GL equal to 9.21 into 0.1 into 0.921. This is the answer. Now another problem, number 4. So so in this particular problem I have used one formula, that is e to the power x equal to 16 L sat by dA. So this is the gain, and this is the saturation length of the amplifier, and this is the diameter of the gain medium. So the derivation of this formula is not required, but this formula is a important one to calculate this kind of, to solve this kind of uh, problems. So again, see another problem that uses this formula to calculate the gain. So the problem is a high gain pulse laser amplifier of length 1 meter and diameter. So the high gain pulsed laser amplifier of length 1 meter and diameter 0.01 meter. Diameter of 0.01 meter has a single 100% reflecting mirror located at the end of the amplifier. The laser is found to have a beam emerging from the other end of the amplifier with an intensity just equal to I saturation. If the mirror is removed, by what percentage would the gain have to be increased in order for the beam to reach I sat at the end of the amplifier under the same operating condition? So basically what happens is that it will only so basically there is only one mirror. So the problem is very straightforward. This is the gain medium, then there is a mirror. So the beam is actually traveling this path twice. Okay, so this has a distance of 1 meter and the diameter is oh, the diameter is 0.1 meter. Okay, so this mirror has a 100% reflectivity, and so the problem is that this beam is actually traveling twice the gain medium, but if this mirror is removed, then it will only pass the medium once, and then it has to have the same gain as it has had in the previous configuration, that is the mirror was there. So basically we have to equate the gain after two passes equal to the new gain for the single pass, and we have to find the gain increase. Okay, so we'll start with that e to the power g12. So g is the gain, 2l is the two pass in the gain medium, which is equal to 16 2l t square. So here it is mentioned that after two passes the gain actually reach the the intensity is just equal to I sat, so it just saturates the value, so it will be 6. So we can use this formula and write 16 multiplied by 12 by d whole square, then 16 to 1.1 square 6.4 into 10 to the power 3. So G2L equal to ln of 6.4 into 10 to the power 3 which is equal to 8.76. Then G equal to 8.76 by 2L, which is the L is 1 meter, so 2 into 1, that is 8.76 by 2, that is 4.38. Now again we will calculate the gain for single pass. That we will have the same procedure, but here it will be GL. The 2 is missing because here the beam is traveling only once through the gain medium. 16 L, again there is the 2L is replaced by L, equal to 1.6 into 10 to the power 3. So GL equal to Ln 1.6 into 10 by 3, G equal to 7.38. Okay, so now the gain increase equal to 7.38 by 4.38 equal to 1.68, which is a 68% increase. So basically here we need to have or obtain 68% increase in the gain in order to achieve the same ISAT value, but with a single pass in case instead of double pass. Okay, so here is
Yes, sir.
one reminder, that is this all this okay, because in the last class people were so bothered about the videos and the notes that I had to remind this thing. So again I will just do two more problems, that is ex5. So here the problem is this is a problem considering a helium neon laser with a gain length of 0.2 meter is installed in a 2 mirror cavity having mirror reflectivities that is of 99.9% and 98%. What would be the single pass gain in the laser tube if the discharge current is sufficiently high for the gain to be 4 times the threshold value. So this is the problem statement, that is there is a helium neon laser with a gain length of 0.2 meter which is installed in a 2 mirror cavity having mirror reflectivities of 99.9% and 98%. So the question is, what would be the single pass gain in the laser tube if the discharge current is sufficiently high for the gain to be 4 times the threshold value. So there is another important statement that is at the end of the question, that is, assume that there are scattering losses of 0.2% per pass with in the cavity. So this is an important statement, that is, there are scattering losses present in the cavity. So there is already 0.1% transmission loss present in the for one mirror, and for 2% reflection loss present in the another mirror, and then there is another loss, that is 0.2% scattering loss per pass in the cavity. So transmission plus absorption loss point 99.9, so 0.1% and 2%. So this is for mirror 1, this is for mirror 2. So here I am writing transmission and absorption loss because there are three types of phenomena that can happen after shining a light on a mirror. So that is one, that is three or four things can happen actually. So one is, that is, it is reflecting back, so that is the first phenomena. Then the second phenomena is that it is transmitted through the mirror, but due to it is the mirror has a specialty of reflecting beam, so the transmission is generally very less. Then there is absorption, because whenever we shine a light on any surface, the light is absorbed by that surface of the material, so that is the absorption. And then there is a scattering, the scattering, so the light will be scattered by the surface, so it will not reflect it. So apart from reflection, there are three phenomena: transmission, absorption and scattering. So when we are mentioning the reflectivity of a mirror, it means that the rest of the beam is either transmitted or absorbed, or both of them. So here the reflectivity is mentioned 99.9% and 98%. That means the rest of the beam is either transmitted or absorbed, or both of them happen. So 0.1% is lost in transmission and absorption, and for the second mirror 2% is lost in the transmission and absorption. And then there is scattering loss 0.2%. Okay, so now these are the values. Now we'll just write down the parameters first, that is given in the problem. L equal to 0.2 meter, reflectivity for the first mirror is 0.999, reflectivity for the second mirror is 0.98, A1 equal to A2, that is for, so A1 equal to A2 equal to 0.002. So if the scattering loss is different for different mirrors, then we'll have different value for A1 and another value for A2, but here the scattering loss for scattering losses of 0.2% per pass, that means that both of the mirror has same scattering loss. So A1 equal to A2 equal to 0.002, and then there are in the general case, in the general case we have multiple parameter R1, R2, A1, A2, GTH, alpha and L. So we know the value of L, we know the value of A1 and A2, which is equal to 0.002. Then R1, and we also know the value of R1 and R2, and then we need to find the GTH, and then there is the alpha. So as there is nothing mentioned in the problem about the absorption in the medium, so we'll consider alpha equal to 0. Okay, so the GTH, so what is the formula? So GTH is 1 by 2L ln 1 by R1 R2 1 minus A1 1 multiplied by 1 minus A2 plus alpha, so alpha equal to 0. So this part of the formula will be used. So GTH equal to 1 by 2L ln 1 by R1 R2 1 minus A1 1 minus A2 plus alpha, which will be written as 1 by 2L ln 1 by R1 R2 1 minus A whole square. Then we'll just put the values 2 into point ln 1 by 0.999. So this is on reflectivity, then multiplied by 0.98, then 1 minus 0.002 whole square. So after simplifying this, it will be 1.26 into 10 to the minus 1. So this is the threshold gain. Now what was the main problem, that is what would be the single pass gain in the laser tube if the discharge current is sufficiently high for the gain to be 4 times the threshold value. Okay, so this is the threshold gain. So the gain is G0 equal to 4 GTH is 4 into 1.26 into 10 to the minus 1, it is 5.04 into 10 to the minus 1, which is basically 0.504. Now I by I0 equal to e to the power G0 L e to the power 5.04 into 10 to the minus 1, 0.504 into 0.2 is 1.106. So this is the single pass gain e to the power g naught l. So we need to calculate this quantity in order to find the answer for this problem. So here this is a very interesting problem because this problem has every kind of loss that is possible in the gain medium. Only one loss is excluded in this problem, that is this alpha. So the gain is not the gain medium is not absorbing any power. So I'll just briefly describe the problem again. So here there is a laser which has a different 2 mirrors with different reflectivity, and then there is scattering loss of 0.2% per pass within the cavity. So we just use this formula for threshold gain. It is 1 by 12 ln 1 by r1 r2 1 minus a1 1 minus a2 plus alpha, and put all the value, and then we find out the I by I naught, it is e naught e to the power g naught l, and we find out that I by I naught, this ratio is 1.106. Then another problem, that is here this statement of the problem is very big, so I'll just write down the important values. So a hypothetical rod of length 0.15 meter and diameter is 5 mm is coated with a 100% reflector at one end of the rod and no reflector at the other end of the rod. So this is basically a one mirror type of problem, because at the one end there is a mirror, but at one end there is a 100% reflector coating, and in the other end there is no reflector at the other end. So it has an anti-reflection coating on that end. It operates at a wavelength of 800 nanometer and is homogeneously broadened. Operating wavelength 800 nanometer, and it is homogeneously broadened. The upper laser level has a lifetime of 20 microseconds. Tau u equal to 20 microsecond. Now the pumping flux is such that the laser is at threshold, and the population difference between the upper and the lower laser level for that condition is measured to be 1 into 10 to the power 26 per meter cube. 1 into 10 to the power 26 per meter cube. What is the intensity of the laser at the output end of the rod? So this is a different problem, and the formula is discussed in the NPTEL lecture videos, not in the problem solving session. So I'll just use the formula. So there is one reflecting coating, so that means that the rod is it is just traveling just twice distance. So 0.3 meter, this is 5 mm. Now lambda equal to 800 nanometer, that means 1.5 eV. Then delta n equal to 1 into 10 to the power 26 per meter cube. Then tau equal to 2 into 10 to the minus 4 seconds. So these are the important parameters given in the, or important values given in the problem. So it is a very good habit to write all the important values that is provided in the question, so that you have an idea of what kind of information is provided to you. So then it was sigma delta n L equal to 16 L by D whole square into 16.3 by 0.05 square, that will be 0.76 into 10 to the power 4. So sigma delta n L equal to ln 5.76 into 10 to the power 4, that will be 10.96. So sigma, that is the cross section, basically 10.96 by delta nl equal to 10.96 by 1 into 10 to the power 26 1 into 10 to the 20 10 to the 26 into 0.3 3.6, which is 3.65 into 10 to the minus 25 meters square. So this is the cross section. Now we will calculate the ISAT, the saturation intensity. So ISAT is equal to 2. Okay, so ISAT equal to h nu by sigma tau u, or just simply tau. So the h nu is the energy at 800 nanometer range. So the 800 nanometer is corresponding to, okay, so I should not write equal to here. So 800 nanometer correspond to 1.55 ev. 800 nanometer correspond to 1.55 electron volt. So H nu equal to 1.55 electron volt, then sigma is equal to 3.665 into 10 to the power minus 25 minus 25, then tau u equal to 2 into 10 to the power minus 4 equal to 2 into 12 into 10 to the power 28 eV per meter square second. So now this unit is a very odd unit to use in this kind of problem, electron volt per meter square per second. So we'll just convert this into joule or watt. So in order to convert that, we will use 2.12 into 10 to the 28 eV meter square second into 1.6 into 10 to the minus 19 eV joule per eV. So this is the 1.6 into 10 to the minus 19 is the value of the electron charge. So we'll just multiply that with this and we'll have 3.39 into 10 to the 3.39 into 10 to the 9 joule per meter square second, which will be 3.39 into 10 to the 9 watt per meter square. So this is the saturation intensity. Okay, so today mainly I have discussed about the cavity mode. So there is this a short recap of whatever discussed in today's problem solving session. So here I have discussed about the cavity modes, where we have counted the cavity mode, that is by solving the oscillating function in space that is bounded in a Lx, Ly, Lz volume. Then in order to solve that, we need to we have two conditions, that is the field to be periodic in L and also 0 at the boundary. So from that we have calculated the mode, and that is the number of modes is calculated by calculating the volume of the octant, and that is this thing 4 pi by 3 lambda cube v. Now that is then the lambda is uh, replaced by the value c by eta nu, and then the volume is 4 pi n eta cube nu cube by 3c cube v. Then the mode density is given by this one 8 pi eta cube nu cube 3c cube, and then the mode density for the frequency interval nu and nu plus d nu is for 8 pi eta cube nu cube c cube by c cube. From there we have derived the Rayleigh-Jeans formula. Then we have used the I intensity, that is u nu multiplied by c by eta. Then we have just calculated the power. Then we discussed about the laser with two mirrors. The two important parameter for this laser with two mirrors to actually work is that the net gain per round trip and sufficient gain duration. So net gain per round trip should be greater than the loss suffered in that round trip, and the loss is consist of three types of loss: transmission, absorption, and scattering loss, and the gain duration needs to be higher. So this is the net gain per round trip e to the g nu naught 12, and this is the threshold gain. That is, so when the in case of threshold gain, the gain should be equal to the loss suffered by the in that round trip. So that is r square e to the power g th 12 equal to 1. So here for a further clarification I can write that the beam that is incoming to the cavity, it has a intensity I naught, and it will suffer two reflections. So it will, after two reflection, it will be r square, and then after that it will have a gain e g th 2l. So this is the thing, and this will be equal to I naught. So then from this equation, if we simplify, that I naught will be cancelled out at both sides, and will be left with the equation r square e to the power gth 12 equal to 1. From that we will get gth equal to 1 by 12 ln 1 by r square. So in order to be intensified, the g will be greater than gth. So, and this is a very simple case where the mirrors have same reflectivity and there is no other loss apart from the reflection. So, but here this is a much more general case where a1 and a2 are the scattering loss from the a1 and a2 are the scattering losses from two mirrors, and r1 r2 are the reflectivity of two mirrors respectively. And there is also absorptions present in the medium, that is alpha. So in that case the equation will be changed to this big equation, that is r1 r2 1 minus a1 1 minus a2 e to the gth minus alpha multiplied by 12 equal to 1, and from that we will get this formula. So then I have mentioned some amplifier parameters for various lasers. So the general case is used here, where the cavity or the mirror has different kind of reflectivity, that is 90.9% and 98%, or also it has a scattering loss of 0.2% per pass. So this particular example is very important in this particular segment of the course. So in the next class I will discuss about the matrix method, which I have already discussed in one of the previous problem solving session, but in that class I'll show some example of matrix method and how to use the matrix method. So by matrix method I will calculate the stability of a resonator and also show how this method is used to solve the problem and how easy this method is actually. So matrix method is basically ray optics or geometrical optics. Okay, so any doubt regarding today's class?
No, sir, I don't have any doubt, sir.
Okay, so one thing I'll just repeat again. If you want to get this video or notes, you can find that in the NPTEL portal. Okay, so the
Yes, sir.
person who asked this did not join today's class, but uh, as you are here, so I'll just inform you. So have you checked
Yes,
the
sir.
videos and notes?
Sir, I haven't checked the notes, but videos, yes, sir.
Okay, okay, that's good. So
Yes,
are
sir.
this
I'll check them.
problem solving session helpful?
Yes, sir. So this is my first session because last 2 3 sessions I couldn't attend. That's why,
Okay,
sir. So yes, sir. It was. I mean, it is very useful. Thank you, sir.
okay, okay. Thank you for joining today's call. I'll just end today's session. Okay.
Thank you, sir.
Thank you.
Sir, can I leave the session?
Yeah, you can leave this.
Okay, sir. Thank you. Sir.